Here's our notes for 6.1.3 for integrated 2. Just want to kind of blend a little bit the special right triangles and trigonometry. So I want to show you something that I think is fairly interesting. If we take a look at this triangle here that's been given to us and using the angle theta, I'm going to go ahead and use this idea of trig to help myself out. But I'm also going to use the idea of the Pythagorean theorem. So let's do the Pythagorean theorem first. So let's kind of ignore that theta for the time being, since we know with Pythagorean theorem, the only thing that we definitely need to make sure that we have is a 90-degree angle, which we do. So I think we're good. All right, so with Pythagorean theorem, we're going to take the two legs, which we know are x and y in this picture. So I'm going to take the first leg plus the second leg is equal to hypotenuse squared. Okay, really not much to do here. We're just going to end up with x squared plus y squared is equal to 1. Doesn't really look like a whole bunch right now, but it's going to in just a moment. Let's get some trig involved here. So I'm going to go back to the picture. Now I'm going to use my theta. So I'm going to identify my sides based off of my theta here. Looks like my opposite side is going to be y. Looks like my adjacent side is going to be x. And looks like opposite the box is going to be my hypotenuse. So I want to write a couple of things out. I want to identify, let's go ahead and do sine and cosine specifically, only because I really care about the x and the y. I don't want to mix them, but I do want to get some sort of a version of an equation just involving y or just involving x. So let's do some trig here. So let's do sine of our angle theta. Okay, well, we know sine is going to be opposite over hypotenuse. So if I do opposite, it's going to give me y over hypotenuse 1. Okay, so it looks like sine theta for this picture is actually going to be defined as y. All right, we're going to come back to that also. All right, let's do cosine of theta. Okay, cosine of theta we know is adjacent over hypotenuse. So in this case, it's going to be x over 1. All right, well, we don't really need the over 1, so let's go ahead and dump that as well. So we know cosine of theta is going to be equal to x. Okay, still doesn't look all that exciting, but it's going to be. I propose that we use these as replacements for the Pythagorean theorem. So this is saying that y is equal to sine theta. So wherever I see a y over here in the Pythagorean theorem, I am going to put a sine theta in its place. So let's go ahead and do that. So I'm going to replace that sine theta right there where the y was located. So I'm just going to put them in their place. All right, I'm going to drop the squared down, drop the equal sign down, and drop the 1. All right, let's see if we can do the same thing with the cosine. So I know that cosine, based off of this triangle, by definition is x. So everywhere I see an x in this equation, I am going to go ahead and replace it also with cosine. So I'll do cosine of theta, replacement, bring down the squared, bring down the plus sign. So there's my replacement. This is one of the first situations, there will be a couple like this in your future math classes, where we're actually able to kind of wrap together the idea of the Pythagorean theorem, which is only side lengths, and trig, which is a combination of side lengths and angles. The key to this, so what really made this actually happen, so let's actually write out this new equation that we've got here. So I am going to use parentheses because that's important. We want to make sure that it's all of cosine that's getting squared and all of sine that's getting squared. And that's equal to 1. So this might not seem like that big of a deal right now, but man, this is going to be pretty huge in your future math classes. This one's big. It's the first time, really, that we can relate Pythagorean theorem with angles. The key to being able to do this, though, is back in the triangle itself. It was identifying the rise, so let's think back to tangent, the rise, which we know is the opposite side, as the y variable. It also allows us to use the run, so which is the adjacent side, as the x variable. But besides that, the magic really comes from the fact that we are able to identify the hypotenuse as 1. That's the big deal here, because if you take a look back at the sine and the cosine, they each had a denominator of 1. But because of denominators of 1, we don't really need them. Now, if it was a 2, it wouldn't be as special because we wouldn't be able to get rid of the 2. So how does this impact us? Well, for now, it doesn't make a huge impact, at least not for our purposes. Let me give you a quick little sneak peek at what's going to be coming your way in future math classes. Let's say I'm actually on the x and y axes. So again, this is future math classes. Let's say I want to build a triangle that starts from the origin and extends to the first quadrant. So let's say it goes somewhere in the x direction, and then it goes somewhere in the y direction. So, kind of making a triangle out of this, I know that this x direction and this y direction. I also know that this point up here, after I've applied the x and the y, technically x comma y. However, if we can force this triangle to either shrink or expand so that the hypotenuse is 1, now the magic happens. We get to be able to do that replacement that we did just a minute ago, where we were able to identify that the x value is actually cosine of some angle. Well, you want to think about the rise was y, the run is x. The angle's down here in the corner. So we could actually say that the x for the ordered pair is cosine and the y of the ordered pair is sine. That's a little tiny sneak peek into future math classes. That is not something that we're going to need to be able to do. The big thing really for these notes was just to relate the fact that you could use sine and cosine to actually getting the Pythagorean theorem and how they can kind of blend together.